Hello everyone, my name is Vikas Panghal. Welcome to this session of AWS IoT Analytics. I am the Senior Product Manager for the service AWS IoT Analytics, and today I'm going to talk about what the service capabilities are and what are the service components, giving you a complete overview about the service so that you can find out for what use cases you would be able to use the service. So we launched AWS IoT back in 2015, where customers started connecting their devices to the IoT platform. And though customers were seamlessly able to connect their devices with AWS IoT, they have got they still had this challenge of getting any meaningful insights from the data that their devices are sending. So some of the customers who are into industrial domain, or our customers who are in device manufacturing domain, they have devices spanning across the globe, and each of these devices are sending huge amount of data. So the question remained was like, how do they generate the value from the data which is being sent from these devices? So for that, we launched a service called AWS IoT Analytics. So AWS IoT Analytics is a service that processes, enriches, stores, analyzes, and visualizes your IoT data, and so that you can generate some meaningful insights from the data which is being sent by your devices. So if you look at the overall IoT data, there are couple of use cases or a couple of challenges that our customers have to go through. The first one is like IoT data is quite noisy or heterogeneous. It contains a lot of gaps or false readings due to intermittent connections, or some of the sensors which are connected out in the field, they are intermittently connected, and as a result of that, they send very noisy data. So this is not something that you could simply connect to your traditional software analysis portals to do the analysis. So you would need to do some structuring to this noisy data. The other challenge was that typically the sensors are tuned to send some specific information, and they often lack contextual information. So how do customers can get any contextual information? What are the primitives they could use to do the data pre-processing along with getting a context for their data? So once they would be able to process the data, they would still need to store that data, and this is a huge amount of data that we're talking about, because there are a lot of devices, and each device may have multiple sensors, where each sensor is sending multiple messages even per second. So that leads to a huge amount of data, and so we need to provide a mechanism for our customers on which they can actually store this huge amount of IoT time series data. And when they have this data, some sort of a data stored, they would actually start doing some analysis to get some insights out of it. So if you look at this overall journey of our customers, AWS IoT Analytics gives all the primitives and provides a fully managed solution to solve all these challenges, and using which customers can actually get the data from the devices and generate a meaningful insights. So all the intermediary activities like structuring of your data, storing it in a data store which is optimized for IoT, and then generating some meaningful insights, all of this would be handled within a single service called IoT Analytics. So let's talk about how this service works. So as you see here, AWS IoT Analytics ingests data from AWS IoT through MQTT topic. So if you have defined MQTT topic, the same topic can be defined in channel, which is the first component of the service, and you can start ingesting the messages from the devices. In addition to that, if your data is already available in your S3 bucket or Kinesis or your own on-prem data store, the service gives you an ingestion API. You can use this API and get the messages directly into the channel. So at this stage, when the messages are being sent to the channel, they are at the raw form. So as we discussed in our previous slide, there should be some primitives for our customers to pre-process this data, or sort of an allowance to do in ETL. So this pipeline, which is the next component, would allow customers to do that pre-processing. So the pipelines have three inbuilt activities. One is filter, the other one is transformation, and the third one is enrichment. So using the filter activity, customers can actually filter out any erroneous data or anything that they do not need for their analysis. Using the transformation activity, they can do some mathematical transformation or any conditional transformation. So, for example, if you wanted to transform your data from Celsius to Fahrenheit, you can do that in the transformation activity. And using the third activity, which is the enrichment activity, you can actually enrich your messages from MQTT topic filter, device shadow, or registry. So these are the three activities that the pipeline provide. But if you have requirement for your advanced analysis, advanced pre-processing, and if you wanted to enrich your messages from your own on-prem store, you can use your own custom Lambda function within the pipeline to do that advanced pre-processing. So once you do the entire structuring of your data within the pipeline, the data is being stored into the data store, as we see here. So this data store is fully IoT optimized, which means it takes the data as the devices send, usually in the time series fashion. So this data store would be partitioned by time, so that you would get very faster query response times when you run on this data store. And again, it is a fully managed data store, so you do not have to sort of manage the partitions, or you do not have to bother anything under the hood. So the service takes care of everything. So once the data store is created, you could run a SQL-like query to create a data set, which is something that you could visualize in QuickSight if you have an account with QuickSight, or you can use our APIs, using which you can export the content of your data set, and you can use your own third-party application as well if you have been using any third-party visualization application. So in addition to the simple descriptive analysis that SQL query provides, the IoT Analytics service gives you advanced analysis tools as well. So the service provides you Jupyter notebooks. So using these Jupyter notebooks, you would be able to do advanced analysis. So Jupyter notebooks are very common industry standard for Python, for writing Python code, sort of Python editor, and you can write your advanced analysis code in Jupyter notebook. So the service provides you two types of notebooks. One is the blank notebook, using which you can actually write your own ad hoc code and perform analysis or even visualization. But the service is also providing you a couple of templates which are very common in IoT world, like predictive maintenance, anomaly detection, forecasting, or segmentation, if you will. So you can use these templates and create an analysis, or generate insights using those templates. So as you see, from the point where the service gets the messages, which are raw, to the point you would be able to generate insights, everything is handled by a single service called IoT Analytics. So in our next slides, let's dive deeper into each and every component of the service. So let's start with the channels. So channels are the entry point to AWS IoT Analytics. So you can ingest messages from any custom source using the ingestion API, or there's a predefined connector available between AWS IoT and channel. So you can use the MQTT topic, using which the service will start getting messages on whatever the topic you have specified there in the channel. So the channel also takes the messages based on JSON or binary format. Typically, we have seen most of the devices are sending messages in JSON. So, but there are some cases where devices are sending binary data. So the channel will take both of these formats as for the data. If you're using binary as a format to input the data into channel, then you might want to use a Lambda function within your pipeline to convert it back to JSON, because your activities would work on the JSON format. And these channels are highly scalable, which means that as and when your fleet size grows, These channels will also be able to ingest the varying number of messages being sent to the service. So you won't be hitting any throughput issues with these channels, because channels will automatically be scaled based on your fleet size. So let's move to the second component, which is pipelines. So the pipelines provide three key activities. One is filter, then the enrich, and then the transform. So you can use filter to conditionally, purge or remove messages or any outliers. And then similarly, you could use transformation to do any mathematical or conditional transformations. And you can enrich your messages using enrich activity, especially from MQTT topic, device registry, or device shadow. But if your requirement is actually more custom than what the pre-configured activities do, then you can use the custom lambda function, and you could do any advanced transformation or any advanced enrichment, such as getting the messages out of your geolocation site or weather data, or maybe your own CRM solution or any on-prem data store you have. And again, these pipelines actually scale based on the number of fleet of devices, so that you won't have any bottleneck in terms of pre-processing your data. The pipelines also provide you a simulation activity, which would actually simulate one of the activity that you select, and it will take the sample data and do the transformation, and it will show you the result, so that you can be rest assured whether you have configured your activity properly or not. In addition to that, pipelines also gives you reprocessing capability. So what reprocessing would do is it would allow you to go back in time and again reprocess your already received data, just in case if you realize that you have done some changes to your pipeline, and now you wanted to go back in time and reprocess all your data that you have received for last 6 months. So you can do that as well within the pipelines, by choosing the reprocessing capability of the pipeline. So the next component is the data store. So data stores, we have IoT optimized data store to store the time series data. It is partitioned by time to give you a faster query response time. And we allow you to set up your own retention policy, so that you can choose to specify till when you want to store this data. But you can set it up to indefinite as well, in which case we will simply keep whatever data is being sent to the data store, and we will not gonna delete it. Again, you are the owner of your data store, so you would specify any retention policy based on your use case and based on your preference. So the next is the data sets. So the data sets basically are the result of a SQL-like query that you run on a data store. So you can schedule these data sets, or you can run them on ad hoc basis. And these data sets basically returns into a result of a tabular format, which you can connect it with the visualization portal of Amazon, called Amazon QuickSight, and you can visualize the dashboards using these datasets. You can also use these datasets in the Jupyter notebooks for advanced analysis. And the service provides you a SQL query editor, which you can use to write your own SQL queries, or edit those queries if you need to. So the next component is Jupyter notebooks and templates. So the service provides you, like I said, blank notebook or the pre-configured or pre-authored templates. So all of these Jupyter notebooks or templates are actually running on and are hosted on notebook instances, which are powered by Amazon SageMaker service. So whenever you run these Jupyter notebooks, the service asks you to create a notebook instance, which is basically a type of an EC2 instance that you can choose, and on which all these Jupyter notebooks or templates will be running, so that you can persist them for your multiple sessions, and unless you are actually terminating that notebook instance itself. So the service gives you a couple of pre-authored notebook templates. So the service has 6 notebook templates, and all of these 6 templates are primarily about predictive maintenance, anomaly detection, fleet segmentation, and forecasting. So these templates are using different algorithms under the hood. So some of the templates are using LSTM, whereas other could be using neural network, or logistic regression, or maybe the other one would be like k-means for clustering or segmentation. So you can choose whichever notebook template would work well for you. So all you have to do is you have to pick in your data set, connect your data set with the Jupyter notebook, and the console drives the experience seamlessly for that. So once you connect your dataset with the Jupyter notebook, you would have to do some minor changes, because these notebook templates are pre-authored based off sample code. So you might want to replace that sample code or sample columns with the actual dataset columns, and that's it. So you do not have to actually modify the algorithm or any other rest of the code, and you should be able to get started with the pre-authored code or pre-authored template. So this was all about the components and the overview of the service, like how different components interact with each other, and what are the components of the service. So I'm just going to give a quick recap. So the service has 5 components, starting from channels, pipelines, data stores, data sets, and then Jupyter notebooks and templates. So you can use channels as an entry point, store your raw data, and again you can specify your retention policies for channel as well, up until what time you want to store these raw data. And then use pipelines to do any pre-processing, and use data store for pre-processed data, and based on the data which is available on the data store, you can run SQL like queries which would result into data sets, and then you can visualize these data sets or use them for advanced analysis in Jupyter notebooks and templates. So this is what I just wanted to quickly talk about as a preview, as an overview of the service. And now we will be actually spending some time on the demo, wherein we will get some data into the service, and we'll show you how the data flows through different components and what you can do using this service analytical capabilities. Thank you so much for attending this session.
Hello everybody, I am Philipp Sacha. I'm working as a specialist solutions architect for IoT at AWS, and I will walk you through a short demo regarding AWS IoT Analytics. This demo is based on a series of Jupyter notebooks, and I will show you how you can explore your data set and a short example for detecting anomalies. So what the base for this demo? The base is of course some messages that are coming in from sensors into AWS IoT, and I want to show you the kind of data that these sensors are sending to AWS IoT. Therefore, I will subscribe to a topic in the AWS IoT console, and here you can see that our data incoming into that service. You see that the data have different formats. So we have one sensor that is sending less information than the other sensor, and now we need to transfer these sensor data to AWS IoT Analytics into a channel. And we use a so-called topic rule in AWS IoT for that. With a topic rule, I select all the data that are arriving on that channel, and I transfer these data to an AWS IoT Analytics channel. Let's have a look at the AWS IoT Analytics console. You can see here I've created already some channels. I've created also pipelines and data stores. You can create these channels, pipelines, or data stores here in the AWS IoT console, or you can also use the API for that. In this example, also a Jupyter notebook. So I will start with the first Jupyter notebook that I have. That Jupyter notebook is called Shared Analytics, because I define here variables that I will use also in the other notebooks. That means I will share these variables so that I have no need to define these variables again and again and again in all the other notebooks. So to call the APIs from my notebooks here, I need to attach an role to the SageMaker instance where the Jupyter notebooks are running on, and I need to allow several actions so that my whole setup will work. So I will first show you an example how you can also create an IoT analytics setup through the API. That means here through a Jupyter notebook. First of all, I will define my variables here, and then I have created a notebook that is called Create Analytics Setup. So first of all, I will import Boto 3. So this is all Python stuff, and Boto 3 is a library for Python that makes it easy to call APIs within AWS. So I will import this library, then I will restore the config that I have defined in the shared analytics Jupyter notebooks. Now I will create some Boto 3 clients for IoT analytics and for calling the IoT API. And now I will create a data store. As you can see, I have here already an IoT web data store and a workshop data store created. And I will create another one that's called IoT WebDay 2 data store. So that means I will first create my data store. I have to reload the section of the console. You can see here the data store was created. Then I will create a channel. So channel is also created. And now to glue the channel and the data store together, I will create a simple pipeline that simply routes all messages that are coming through the channel to the data store. Okay, now you can see I have also created the pipeline. And now I will create a data set. I will select all the data that I can find in my data store as a data set. Okay, already created. Then I can create also dataset content. Okay, and now I have to create a topic rule so that all the data that are coming in on my topics are transferred to AWS IoT Analytics. Okay, so you can see that's really easy to create all the stuff, even from Jupyter notebooks. And let's have a look at the AWS IoT Analytics console. Here in channels, you can see now we have an IoT WebDay 2 channel. We have the related pipeline, and we have the data store. And you can see here also we have created datasets. Okay, but I want to show you also how you can explore some data and how you can probably detect anomalies in your sensor data. And therefore I have already prepared an IoT WebDay data set, and I have already ingested some data. So I will switch back to the shared analytics notebook and now use the other setup for IoT WebDay. Then I will create that configuration, and now let's explore our data set. So first of all, we will import some libraries that we use. Then we will define some global variables here in this Jupyter notebook. Again, because we call the API from IoT Analytics, we need to create a Boto 3 client for that. And now we will create dataset content. So that means we will initialize that the content is created from the data store where the data is stored. This can be done in this case here ad hoc, or you can also do this on a scheduled base. But for that example, we will do it ad hoc. Okay, and now we need to get content from our data set. I will start to get content from our data set with this code here. So what the code does now is it compares the time when we initiated the creation of the dataset content with the time of the dataset that is already present. And if as long as this while loop sees old data, it will wait some seconds and look if the new dataset content has been created. So this should take some seconds, but as soon as the dataset content is created, we will get here another output in our Jupyter notebook. Well, you can see here, amongst other information, I get a so-called dataset URL. And from that dataset URL, I can download the data that are now in my dataset. This is already done here within the code. That means I will read the CSV here from the URL, from the dataset URL, and put it into a so-called data frame. So now let's do some real basic stuff. First of all, we look at the shape. The shape means we can have a look at how many rows and how many columns my dataset has. So let's have a look. Okay, quite nice. We have nearly 20,000 rows of sensor data and 8 columns. So we can also have a look at the first lines or the last lines of the data sets. So let's have a look at the last 20 lines of this data set. And here you can see the data from that different sensors. As you can remember, we have different sensors here. The sensors are identified by the column thing ID. So we have different ones here with different data. For example, one sensor is also sending geolocation data, what the other data set is not sending so far. So now we have seen some basics from our data set, and now we can switch to the next notebook and can have a look also if we can detect some anomalies here in this data. So what we will use here is an algorithm that is called probabilistic exponentially weighted moving average. And the idea is here to detect anomaly in a context to other data. So that means in case of our temperature sensor, if a temperature sensor shows a temperature from, for example, 10 degrees Celsius, that's not an anomaly itself. But if you put it in a context that you have a temperature measurement, for example, in a room around 20 degrees Celsius, and then suddenly the temperature drops, for example, to 10 degrees, only for one point that is measured. So then there might have been something gone wrong with the sensor. So first of all, we will also import a lot of libraries here that we use in this Jupyter notebook. We will also restore the shared variables that we have created in the shared notebook. And also we need to create again our Boto3 client. Then we need to create again for this notebook dataset content, because the dataset content is not shared about our notebooks. we have here the same loop to wait for dataset content as we had in the Explore dataset notebook. And now we have to wait again a little bit until the dataset has been created. Then we will get back our dataset URL, and we will also then load this dataset into a so-called data framing. So this is the same code like we used in the Explorer dataset notebook. So we have to wait a little bit longer here until the dataset has been created. So it uses at a maximum 40 tries and waits between each try 10 seconds. So let's have a look. We have the dataset URL. That means our dataset has been created and loaded in the data frame. Now we need to set some parameters for that PEVMA algorithm. So that's really easy. And now we define a function to generate this algorithm. Okay, so what we do now here is we will create this algorithm for one of the devices that we have connected to AWS IoT. So this can take some time. We have around about 20,000 lines in our data set, so it should not take too long. We have tested it also with around about 700k lines. Then it takes with a small instance here around about 20 minutes to calculate this algorithm. But here we are much more faster because we don't have so much data, and we can see here we used around about 12 seconds. We will do the same exercise for another sensor that is connected to AWS IoT and what is ingesting data into our data set. So we have again to wait a little bit here. And while we are waiting, we can have a look at the next cell in the notebook. This is a function definition that visualizes the data that we got from the data set. It's already done here, and we need to define the function here. Okay, and in the next step we will visualize the data from our first sensor. Okay, now you can see here we have in blue the actual value. That means that the value that was present in the data set, that was a value that the sensor delivered to AWS IoT. We can see here this moving average. So you can see that the average is also moving with the temperature measurement. And we have a boundary here for the moving average. That means from around about 30 degrees to around about 27 degrees. That's simply normal for this use case. And here you can see there we have a measurement of around about 10 degrees Celsius, what is marked as an anomaly, because it could not be, if you see here in all the time series that we have, that the temperature in a room drops suddenly from 1 second to another around about 20 degrees and comes up again. So, and this is a method to detect anomalies in your data. We can also use, for example, the other sensor that we have connected. Here you can see it looks a little bit different really. So the sensor delivers other data, but we can detect here an anomaly here with the sensor, so we can think it's operating normally. Okay, so far that was my short demo. If you have any questions, please let us know, and we will answer them then. Thank you.